Good afternoon, everybody. Welcome to our August webinar on THM removal. This is our monthly webinar series that we do every month and started about a year ago. We're going to keep it going until we run out of steam, which would probably, knowing us, will be never. We're going to have Ethan Brook up next. Before he starts, a couple housekeeping things. A certificate of completion will be sent out at the end, then tomorrow after the webinar. We also, at the end, the last slide will be a QR code / website URL to claim CEU credits. It's not available in all states. The states are listed at the top of the form, so please take a note of that. During the presentation, there is a questions section in the GoToWebinar app. Feel free to ask any questions anytime. Ethan will get to them at the end, so stick around to the very end and he'll answer all those questions as much as he can. If he can't get to them, we'll send out emails addressing all those questions. Ethan, it's all you, buddy.
Oh, thanks, Mike. Howdy, folks. Ethan Brook here, and welcome to the latest webinar series, as Mike was kind of introducing. Just by way of introduction, my name is Ethan Brook. I'm a senior product manager and a regional sales manager for Clean Water One. And today we're talking about a topic that's near and dear to my heart, trihalomethane aeration. This is a technology that I've been involved with since I was in grad school back in, finished that up in 2009. And I was really lucky in grad school. I got a great thesis topic and had a really talented team to work with. And we did a bunch of research basically showing that trihalomethanes are volatile and that if you create the right conditions, you can volatilize them off after they form. We looked at a few different types of aeration, including diffused aeration, spray aeration, and we ended up really kind of, after I got to PAX, we ended up doing a lot of surface aeration. So we'll review all these different types of aeration technologies to strip THMs today. We'll go through the science of trihalomethane removal. And but before we get a whole lot further along, I wanted to kind of introduce Clean Water One as a company. We're doing a lot of different stuff these days. Out in the distribution system where we do our THM stripping, we also have some adjacent technologies, mixing for destratification, thermal destratification. We'll talk about that a little bit today. We also do a lot of residual boosting. So if you're experiencing low residuals out in your edges of your distribution system, that's another thing that we can help with. And we really, in our company, have a lot of deep expertise in distribution system water quality. For example, I'm the former chair for CalNAB AWWA's Distribution System Water Quality Committee. My counterpart in Southern California, Kevin Sanner, rolled onto that leadership role, and I think he's rolled off of that now as well. We've got Dr. Robin Giguère, who is kind of our head of innovation. He does a lot of hands-on work out in the distribution system with customers, and so we really see ourselves as trying to drive innovation, and we're focused on this big idea, which is moving treatment out into the distribution system, getting closer to the tap, really allowing ourselves to focus on areas of the distribution system where we've got water quality problems. But we don't just work out in the distribution system. We do a lot of other work these days as well at Clean Water One. We do on-site hypochlorite generation with the microchlor system. We do polymer activation with PolyBlend and DynaBlend. We do controls integration, and we have a fantastic panel shop this is kind of a more recent purchase with ICS Online. They're located out in Ripon, California, out in the Valley. Really excited to have that team as joining the Clean Water One family, so that we can get even deeper into controls, programming, SCADA integration. This is a place where we really shine. And we also recently picked up a company called IMS Integrity Municipal Systems, where we do odor control, chlorine gas scrubbers, fluoride feed systems. Another just great company, and we're growing fast these days, and it's a really exciting time to be part of the Clean Water One family. And just in general, it seems like our industry is doing really well. We'll get into some details next. So here in California, where I am, California has experienced a lot of challenges with distribution system water quality over the years, and it's really driven by the coastal communities in California, Los Angeles, San Francisco. These guys are getting their water from far away, and it comes out of the Sierras, which is a couple hundred miles inland, and it comes across the interior valley of California in aqueducts. And these aqueducts are open to the atmosphere. It's dusty out there. And so, a lot of the water quality that's ultimately getting these big metropolitan areas is not that awesome. And so back in the 90s, California made a hard decision, kind of staring down, the disinfection byproduct rules that were coming in. And a lot of these big municipalities have switched over to chloramine. So chloramine disinfection, obviously different from free chlorine disinfection. It's a much more selective oxidant. You don't have as many issues with disinfection byproducts, but it really comes with a whole host of new problems around chloramine degradation. And so, you form this chloramine, monochloramine molecule, it comes apart, and then you've got free ammonia in your water. It's a food source for nitrifying bacteria. So, we've solved some problems here in California by moving over to chloramines, but we also created some new ones. And so, yeah, chloramines, got a whole host of technology to deal with some of the issues that come with those. Free chlorine is really what we're focusing on today, and free chlorine is still the most common form of disinfection. Free chlorine, you've got a less selective oxidant, and you've got lots of oxidation of natural organic matter or total organic carbon that happens as part of the process. And so you end up forming a lot of disinfection byproducts. There are two regulated DBPs, trihalomethanes and haloacetic acids, and we'll talk more about both of those in just a minute. The history of kind of disinfection byproduct regulation really starts all the way back in the 1970s. And it was then in the 70s that gas chromatography was invented. All of a sudden, we could look at very, very low levels of these organic compounds in water. And so somebody had the bright idea, hey, we got this new technology. Let's see what's in our drinking water. And when they started testing drinking water, they were really surprised to find chloroform in the water. And chloroform is one of the regulated species of trihalomethane. And so if you kind of review the literature from the 70s, there was kind of all this work being done to look at, these trace elements in the water, and a lot of concern that they were running into chloroform. Of course, everybody was familiar with chloroform because that was used back in dentist's office back in the day to knock people out. Ever seen those gangster movies from back in the 40s? Somebody sneaks up with a rag and holds it over somebody's face and then they pass out. That's chloroform. So it was a real surprise that this was kind of naturally, or not, maybe not naturally, but was occurring in our drinking water. And so, again, you look at the literature from the 70s, it's all about kind of quantifying, well, how much of these THMs are we seeing? What else are we seeing? In the 80s, there was a lot of kind of literature published on what to do about it, so much more of a focus on treatment options. And then in the 90s, the focus really turned to regulation. And that culminated in 1998 with the passage of the disinfection byproduct rules. When those passed, Congress wisely recognized that this was going to be a big deal. And so those rules really rolled out over the next 20 years. They weren't fully implemented until 2018. And the DBP rules really make us as an industry have a lot more focus on what's happening outside the plant, which makes a lot of sense because that's where people are actually drinking the water. And so again, if you kind of look back through the history, it's pretty interesting. I published a peer-reviewed paper on the work that I did as a grad student back in 2011. And the paper really, frankly, got a lot more attention than anybody was expecting. And we really showed in the paper that spray aeration would be a more energy efficient way to strip trihalomethanes than diffused aeration. The paper was picked up by the president of AWWA, referenced it in 2014. And the paper has also been referenced in, I think it's AWWA Manual M62 on distribution system water quality. Don't quote me on that. But this paper really did help establish this treatment process as a good way to try to deal with trihalomethanes after they form. When we think about trihalomethane treatment, this slide that I came up with as a grad student is still in the deck. Really is important. So we're going to spend a minute kind of talking about this, because if you've got problems with disinfection byproducts, you can really intercede with any of these symbols that you see here in front of you and have success. So for example, I already talked about how out here in California, we do a lot of chloramination. So we've moved away from free chlorine to chloramines. Now, there are lots of reasons why that's not very popular and is really kind of an option of last resort. Dealing with chloramine chemistry is just a lot more complicated than dealing with free chlorine chemistry. But it's important to note that there are some other things you can do with your disinfectants that might help out. For example, if you're doing primary disinfection with chlorine in front of your filters, somewhat common practice to deal with, filters getting gummed up with organic growth. You might try chlorine dioxide. Chlorine dioxide is a great disinfection or disinfectant. Very popular in Europe. We don't really use it here in the US as much as we could. So that'd be something to check out. Really important, frankly, to point out that from a public health perspective, dealing with the Big Mac is a good idea. When we disinfect water with chlorine, if you think about what's going on, we have chlorine atoms, chlorine molecules that are interacting with these huge, long natural organic or total organic carbon molecules that are these big, long chain molecules. And what's happening is you have the free chlorine atoms. They might snip these molecules into smaller pieces. They're going to attach at various charge locations. And so you end up making a lot of different types of disinfection byproducts. When we think about DBPs from a treatment perspective, we're really focused on the regulated species of DBPs, trihallomethanes, haloacetic acids. But it's really important to understand that those are just the two species that are regulated. And there are literally thousands and thousands and thousands of different types of disinfection byproducts that form as a result of chlorination. And we don't know much about the health effects of those, but we suspect that some of them are probably more toxic than trihallomethanes or haloacetic acids. And if you're curious about that, I would recommend a researcher named David Reckow, publishes out of UMass Amherst. He's done a lot of work on this. And so again, from a public health perspective, what we want to do is, not form DBPs. We want to get that natural organic matter out of our water so that there's really less for the free chlorine to interact with. And so ways that we can do that, probably first and foremost and most important, is enhanced coagulation. So if you're running coagulation flocculation in your plant, that's a place where you can just make a tremendous improvement. And I've got a great example from one of my customers up on the coast in Oregon, who was working with us on a THM aeration system, but it was taking a long time to get funded. So they had some time to really kind of look into different types of coagulants, and they did their homework. They did their jar testing, and they were able to more or less eliminate their problem with disinfection byproducts by switching coagulants. That's something that I hope everybody on this webinar today really takes to heart. Protect public health, do the right thing, do your homework, get that NOM out of the water. Start with enhanced coagulation, do the jar tests, call your coagulation and flocculation chemical distributor, make them come in, make them help you. This is really important work, and it's critical that you do that. Once you've done that, and if you still got a problem, your options start to become more limited. If you want to get NOM out of the water at the plant and enhanced coagulation isn't going to do the trick, you'll be looking at adding another treatment step. That could be carbon activation or granular activated carbon, could be nanofiltration, ultrafiltration, advanced oxidation. I used to do a lot of work over in Barcelona in Spain. Over there, they went all the way to reverse osmosis to get NOM out of the water to avoid disinfection byproducts. All those things will work, and all those things will potentially work very well. The problem is that those are expensive things to do, which is why most folks are really laser focused on the big time arrow. So we all know what happens. The longer the water sits around in the pipes, the worse the water quality gets, and the more disinfection byproducts grow. And we'll look at the next slide on that in just a second. But yeah, so everybody's focused on, trying to trim up the time that the water's sitting in the pipes. And that's a smart thing to do. Strategies there might include, looping your dead ends. I know a lot of folks who are not filling their water storage tanks. There are some pretty significant drawbacks that come with that. We'll talk about that more in a bit. But yeah, really, optimizing your system hydraulics to reduce time in the pipes is something that folks are already working hard on. And frankly, most of that work's already been done. So if there's more to do there, by all means do it. But a lot of times there's just no more we can do to reduce detention time. Which is why stripping THMs post-formation and really focusing on the skull and crossbones here has become a really popular treatment approach. We've had just tremendous success with this technology. And the reason that it's so popular is that it's roughly an order of magnitude less expensive than instituting an enhanced treatment at the plant like granule activated carbon. It's roughly 1/10 of the cost. So important to note that when we talk about disinfection byproducts for the remainder of this presentation, I'm referring to trihalomethanes. I'll try to get that right, but THMs are volatile. We can remove them after they form. Haloacetic acids, on the other hand, are not volatile, will not come out during aeration processes. And if you have a problem with haloacetic acids, you're going to have to look somewhere else in this equation to deal with it. Very limited options to get haloacetic acids out after they formed. So here's a slide that kind of shows what we think of as a trihalomethane formation curve on the bottom. And you can kind of see this first order reaction following a nice logarithmic fit curve here. On the top, you can see what's happening to the chlorine at the same time, and it's also a log, kind of a log fit curve there. But you can see basically as the chlorine is degrading, the THMs are forming. And actually establishing one of these THM formation curves for your system might be helpful. So if you guys ever want to make your own THM formation curve, get in touch. We've got a good procedure to help you do that. And again, understanding the THM formation curve is important because here for this example, we really need to understand if we treat at the clear well, and for this example, what's going to happen out here at the water storage tank. So how much removal do we need early in the system to achieve compliance later in the system? And the way that this works is we want to kind of understand the formation kinetics that are going to be happening post-treatment. And we also want to understand the formation kinetics that are happening pre-treatment. So here we've got a THM formation curve, got this nice log fit. And the first thing we want to understand is, well, have we turned the corner on the curve here? Or have we turned the corner on our formation curve? Have we formed enough of our disinfection byproducts or trihalomethanes that when we remove them, we're going to be able to stay in compliance? So you can't get rid of them until after they formed. So we want to make sure we formed enough of them to institute treatment. Here, looks like, for example, we've done that. But we also need to understand how much additional formation is going to happen after we treat. It's not like the THMs just stop forming. So here you can see for the green line, we've reduced them by 40%. And that concentration that's been removed from the water is conserved out at the end. So whatever specific concentration has been reduced, we're going to see that removal out at the end of the curve. Understanding the science for trihalomethane aeration is fairly straightforward. I think it helps to think about a dissolved gas that we're all far more familiar with, carbon dioxide, to kind of get us into the right frame of mind to understand how this works. So we all know what happens when you pop the top on a bottle of Coke, as we see here. You get this fizz as carbon dioxide is released into the atmosphere. But what's stopping all that carbon dioxide from migrating into the headspace inside the body? You can see there's a little air gap there. Why doesn't the CO2 all come out of solution and just migrate into that little chunk of air that's in there? Well, it's because of something called chemical equilibrium. And these dissolved gases will go back and forth between liquid and gas phase, but in a closed vessel, the air can only hold so much of the dissolved gas, and then it becomes saturated. It can't take any more. And so that chemical equilibrium is described by something called the Henry's constant. And here you can see the Henry's constants for the various types of trihalomethanes. Lots of different forms of Henry constant. So if you're looking at Henry's constants, you need to understand the units that are involved. We like this dimensionless form where all the units cancel out, and so it's just a dimensionless number. For chloroform at a 0.13, what that really means is that at the chemical equilibrium, 13% of the chloroform is going to be in gas phase and roughly 87% is going to be in liquid phase. The more brominated species of trihalomethane have different Henry's constants, and the more brominated we are, the less volatile the THMs are, bromoform being the least volatile with a Henry's constant of 0.02, which means 98% of the bromoform is going to be in liquid phase, only 2% in gas phase. But it's really important to note we can strip all of these, and just that small, gas phase concentration for bromoform is still sufficient for us to implement treatment. We just need to understand, what the speciation of your trihalomethanes are so that we can plan accordingly. It's really mostly about how much air we move. The more brominated species require additional airflow. When we start to take this kind of knowledge of the science and apply it to a water storage tank, first thing we're going to need to do is deal with the diffusional barrier that exists at the top of most water storage tanks. From our work in mixing, we know that most storage tanks are thermally stratified, meaning that there's a hot layer of water that's sitting at the surface of the tank, especially in the summertime. And it's kind of like a rubber raft, as the tank level goes up, the raft floats up. As the tank level drops, the raft drops. That layer of water can be very persistent and get stuck in the tank for many, many months. And despite the fact that it's very old water, if you actually take the time to go in and measure the concentration of trihalomethanes in that layer, what you'll find is that the THMs at that top layer are not that high, because you've got some air exposure there at the air-water interface, and you have some turnover in the top of the tank. As the tank level drops and falls, it pulls air in and out. So if you go and actually measure it, your THMs are going to be a little bit lower at that kind of trapped layer of water at the top. So the first thing we need to do to set up a tank for blowing off THMs is mix it. We need to get rid of that diffusional barrier, start introducing a higher concentration of THMs up to that air-water interface. The key here is strong mixing. You need to refresh that air-water interface at regular intervals to get good removal rates. The next thing we've got to do is deal with the tendency for these tanks to reach chemical equilibrium. And we can do that by adding an active headspace ventilation system. You can kind of see a picture of one of our power vents right there on the right. And the good news here is that you can move a lot of air for not a lot of money. It does not take a lot of equipment or a lot of energy to significantly refresh the headspace of your tank. And once you add a mixer and an active headspace ventilation system, now you're off to the races. Just with those two little pieces of equipment, you can remove roughly 10% of your THMs per day of tank detention time. So we've got mixers dealing with that diffusional barrier, introducing high concentration THMs to the mass transfer zone at the air-water interface. We've got an active headspace ventilation system where we're continually refreshing the air in the tank, making sure that there's very little buildup of trihalomethanes in the gas phase. And then the third thing we need is an air-water interface. And every tank's got one. Obviously, the amount of surface area is going to be quite different if you've got a ground storage tank that's fairly shallow versus a tall, skinny standpipe. So in some situations, the amount of surface area that's present is just not sufficient to meet our treatment goals. And so for those situations, we need to add another piece of equipment, a surface aeration system, to start splashing water around. All we're doing with the surface aerators is just making more air-water interface, more surface area for mass transfer to occur. So you can kind of start to see here the common types of systems: mixer plus power vent. Again, simple as it gets. Mix the water, blow air through the headspace, volatilize off trihalomethanes. Ideal for tanks with significant storage time. And what this treatment technology, mixer plus power vent, really does is it takes the way that we usually think about water. Water age is bad. The longer the water sits in the tank, the more problems I've got, and it turns it 180 degrees on its head. Now, the longer the water sits in the tank, the more treatment you get, and the better your disinfection byproducts are leaving the tank. So for those of you who are keeping your tanks partially empty because of concerns about water age, this will allow you to keep your tanks potentially full again. And that's important these days. And I'll take a minute to just share one story on that topic that's I think about with some regularity. You guys may recall the complex fires, lightning complex fires that hit the Bay Area a few years back. The skies turned Blade Runner orange. It looked like the end of the world. It was pretty grim. And I remember sitting up on the hill in back of my house with my 4-year-old daughter at the time, kind of watching the lightning strikes in August and thinking, wow, I can't believe it. It's going to rain in the summer in California. This is wild. Well, it was pretty wild. And a few days later, it felt like Northern California was going to burn down in its entirety. It was on one of those days I got a call from a customer just outside of the Bay. And I could tell when I took the call that things were not going well for my friend. They wanted me to roll out and meet them at a tank immediately. And so that's exactly what I did. They let me through the police cordon and I could smell the char in the air. They had lost around 30 homes in this portion of the distribution system. And when I got to the tank and said, hey, what happened? Well, we were ready. Fire trucks were all on a line, watching the fire come over the ridge line. And we started, thought we were in good shape, but we lost pressure in the distribution system. And we lost pressure because this water storage tank here was only a third full. And it was only a third full because that's our water quality compliance plan. And so, if they had had a mixer and a power vent on that tank, things really might have been different. And so I hope that doesn't happen to anybody on this webinar today. But it's just so important for you guys to understand you don't need to do that. You don't need to keep your tanks at a fraction of their fill capacity because you're worried about trihalomethanes. We have cheap, available technology that can flip the script. So think about that. Surface aeration. Surface aeration works really well for higher levels of removal, situations where time is not on our side. We need lots of removal and we don't have a lot of time to do it. It also works well if we need to remove a lot of THMs. We can remove with some confidence up to about 65% of THMs. It gets really equipment intensive to remove more than 65%. So just keep that in mind as you start thinking about these systems. Spray aeration. Spray aeration is a technology that we used to do a lot of. We did about 75 spray aeration systems for trihalomethane removal. But what we found over time is that our customers that were putting these systems in were just not that happy about it. They were not happy for two reasons. One, although there's not necessarily a ton of equipment involved, the installation labor to put these things in is significant. And so you're not going to pay as much for the equipment, but you're going to pay a lot for the installation. And then once you've got these spray aeration systems in, you've got these header pipes that are up at the top of your tank, and you've got nozzles. And guess what? Those nozzles are going to clog. So if you haven't figured out how to go and scaffold your tank, get to the nozzles, unclog them, you're gonna have problems over time. And then you've got all this pipe, you got to coat it. It's really not ideal from a long-term perspective. And so after that feedback from our existing customer base, back in about 2015, we really pivoted away from spray aeration and towards surface aeration. And it's funny, I've seen a couple of spray aeration designs come out from consultants over the past couple of years. And, frankly, it's a little disappointing because these systems just, you're not doing your customers any favors here. I'm sure you guys like the extra consulting fees, but it's just not that great of a technology. It's hard for me to say that because I did a ton of work on that technology myself personally and published a big peer-reviewed paper on it. But these days, it's really just not the way to go. So when we start thinking about what these systems look like, we've got mixers, lots of different geometries of mixers. We've got tons of different types of active headspace ventilation systems. We've got ground mounted versions. We've got tank mounted versions. We've got a special coaxial power vent I'll talk about in a sec. Surface aerators. We've got, I think, 3 different types of surface aerators that we field now. You can see one of the stainless steel aqua aerobics aerators that we've had a ton of success with over the years, pictured here. We, in 2015, when we decided to pivot from spray aeration to surface aeration, we partnered with Aqua Aerobics, and Aqua Aerobics is a wastewater treatment company primarily. They designed these surface aerators back in the 60s, and kind of like a car from the 60s, these things are massive, rugged, overbuilt, simple. And we thought that that was attractive because anything that you put inside of a water storage tank really needs to run without maintenance for a long time. we'd like to see these systems run for at least 7 years without a human touch. It's not a place where you want things to go wrong. So we've had a great run with aqua aerobics. Some of these systems also come with trihalomethane analyzers. So we can, for larger systems, it can be appropriate to integrate THM and THM analyzer, implement some active feedback control, turn off these aerators when you don't need the treatment. I'll give you an example of that in a minute. And then we integrate these all with integrated control panels. If you think about it, these are all just motors. We've got motors spinning on the roof for the ventilation system, motors spinning with the mixers. So by having a single integrated control panel with an HMI, we don't burn a ton of SCADA channels, monitoring each of these remotely. We can just have a run, off, fault, and then if there's a problem with an individual piece of equipment, you can go to your local PLC at the control panel to diagnose it. One piece of equipment that we came up with not too long ago to add to our portfolio of active headspace ventilation systems is this coaxial power vent. We were getting into concrete tanks where adding additional penetrations was just kind of a pain. And so we thought to ourselves, I bet there's a smarter way to do this. And we came up with the coaxial power vent. Here we can use an existing roof penetration. We can add a blower on top of that penetration, and we can blow air in through the penetration through kind of like a stovepipe. You can see that here on the left, little stovepipe, blowing air down to the surface of the water. And then we can exhaust the air out through the perimeter around that stovepipe, out through that same penetration. This has been a big help for pre-stressed concrete tanks where we don't want to get into messing with any of the structural integrity of the roof. Already really hit mixing plus power ventilation pretty hard here, but I'll just say that this has been, in my opinion, I think one of the coolest things we've come up with for distribution system water quality in my time doing tech development since 2009. And this case study was really kind of how we started to really figure out just how cool this technology was. We had done a lot of work over in Spain and Barcelona in the early years and had gotten some data back from installation there, kind of saying, hey, you can get pretty good treatment with just mixing plus headspace ventilation. So we started talking about this early on back in 2013, 2014. And we had an early adopter, this gentleman, Andy Hamilton, out in Placer County, California. He put in 7 mixing plus headspace ventilation systems, didn't really have a huge problem with THMs, was just on the border of non-compliance, and he thought, wow, the simplicity of this is very attractive. We put him in, I think it was 2013. We didn't hear from him for a couple of years, and then right before Christmas in 2015, he wrote us a note, and he just kind of said, hey, this is going so well. The equipment's been bulletproof. I've had no issues, and my problem with THMs is gone. I just don't have a THM problem anymore. So it's nice to get a note like that. And so early next year, we kind of headed out to try to quantify exactly what Andy was seeing out in his distribution system. We started with a couple of Clearwell tanks. You can see on the left, 300,000 and 1 million gallon Clearwell. And you can see on the larger tank here, the 1 million gallon tank, we've got a PWM 400 mixer, PPV 400 power vent. Combined horsepower for these two pieces of equipment, 1.25 horsepower. On the right, we've got a 200 small mixer, small power vent, combined horsepower for the 300 gallon tank, 0.75 horsepower. We then went out to his ballpark tank. This is a tank with a much higher detention time, 10-day detention. And again, small mixer, small power vent. And you can see these removal rates are just phenomenal. We were really surprised by the results here. 4-day detention time, right around 40, 45%. 10-day detention time, we got to around 65%. And that's just a phenomenal result for such a small investment of infrastructure and a small investment of energy. And so again, for those of you who are currently not keeping your tanks full because you're worried about trihalomethanes, think about the risk and the reward here. We feel strongly that adding this equipment to your tank is going to put you in a very different place. You're going to sleep better at night, and you're going to be doing the right thing. Here's another case study. This is Colorado Springs. This was a few years later. These guys had a high reading in the summer, and they were really concerned that if they did not move quickly, ahead of their final compliance requirement for the year, they were going to be in violation. So they released an RFP over Thanksgiving week. I remember that well. And they wanted a system in and installed and done by the first of the year. And so we responded quickly. We looked at their data and we thought to ourselves, we can do this with just a mixer and a power vent. And so you can kind of see this is a tall, skinny standpipe, but we looked at the hydraulics and the turnover and thought this is going to work just fine. We put in a fairly large mixer, a PWM 500 at a 1/2 horsepower and a PPV 400 at a 1/2 horsepower. So that's a combined horsepower of 1. And you can see these guys were looking to pick up around 25% removal, and they ended up between 42 and 48%. So just a great result, done a bunch of work with them in the following years. When we first started kind of working out in the distribution system doing trihalomethane aeration, nobody really believed that it was going to work. And, you know, having done tech development in water for, you know, most of my career, this is not a friendly place to do new things. Nobody really wants to do any of this kind of stuff. It's just risky. You know, there's real risk here. This is not a place to try new things, and we understand that. But at the same time, you know, innovation has to happen, right? So in order for us to kind of get over the hump, we really had to put our money where our mouth was, and to actually go ahead and offer performance guarantees for stripping. And so the way that works, you know, we have to agree on a certain number of variables. You can see the operating conditions that are part of our process guarantee on the left. Pretty straightforward. You know, got to know what's the size and shape of the tank. One that's really important for us, for our calculations, is this turnover number. It turns out that the amount of water flowing through the tank is actually a little bit more important than the amount of water that's stored in the tank. So that's important for our calculations. But the way these work, you know, we agree on this stuff ahead of time after the system's installed, and, you know, there are no mechanical issues. Let it run for a couple of weeks, make sure everything's good. We'll take a set of readings with the system off, sample once a day for 5 days, compare that with the THM levels with the system on, and you can see our complicated math down here in the bottom right-hand corner. But yeah, it's a pretty straightforward process, on versus off. We've had some questions on this recently from some consulting engineers. You know, why can't we just measure the tank influent versus the effluent? And the problem with that approach is that you don't capture the trihalomethane formation that's happening while the water's sitting in the tank. So you can be in situations, you know, where you're measuring the influent of the tank and then the effluent from the tank, and there's actually more coming out than there is coming in. And it's like, what's going on here? Well, you got to remember that THM formation curve, and you're constantly forming THMs as the water sits. So this on versus off method is a way to take the THM formation into account. And we've got some really good kind of fairly detailed validation protocols we can share, so you can really understand the math. But it's once you think about it for a little bit, it'll make some sense. As I mentioned, you know, we've had a great partnership with Aqua Aerobics with their floating surface aerators. These surface aerators move a lot of water, and you can kind of see the spray pattern here, where we're making you know, we're not spending our energy to pressurize the water and break it up into lots of little droplets with a ton of surface area. Instead, we're kind of more creating a froth of water. So there's more than one way to strip THMs from a flow perspective. You can spend your energy to make droplets, or you can spend your energy on flow. Turns out, after doing a lot of work on this, it doesn't really matter. You can spend your energy on flow or water. Both work just fine. You'll have good results with what we think of as high flow, low pressure, which is what you see here. You'll also have good results with high pressure, low flow, where you are, again, you know, kind of breaking things up into much smaller droplets. Not a ton of difference in the overall efficiency between those two approaches. Here you can see some of our surface aerators deployed inside of a tank. This tank is over in Australia. I guess the water is green over there. Not sure what that's about, but you can kind of get a sense for you know, the quality of this equipment. This is good stuff. Surface aeration, tried and true. You know, we've done some very large scale surface aeration systems. I'm thinking of one that's going into the ground right now in Canada. I think we've got 28 15 horsepower aerators on that job. So these are systems that can really be deployed at virtually any scale, from, you know, a very small tank to a huge reservoir. Again, if you're putting equipment inside of a tank, you really want to make sure that that equipment is going to be in good shape to run to fail without any human intervention. Here's a case study from close to home for us out here in California, San Luis Obispo. Beautiful, beautiful place to be. These guys have got a 2 million gallon clear well, turning over 5.5 million gallons a day. And they've got high THMs kind of throughout their distribution system. So you can see time is not on our side here. So that'll give you a clue where we're going. But these guys kind of had quarterly issues. They thought they had it licked for a while, but then it kind of came back. So they decided to get after it. Here you can see their water treatment plant. Lovely place to do some work, I'll tell you what. These guys did the right thing. They took some time ahead of time to quantify their THM formation curve. Here you can see we got a little jaggedness in the data, but generally follows this kind of logarithmic fit curve where we have fast formation initially, followed by slow formation as time passes. You can see kind of where we are when we start matching up our distribution system sample data to the THM formation curve. Everything kind of starts to make sense. These sample locations have you know, time, dwell time before we get there that is, you know, falls right onto the curve. So this is all lining up well. After the system is installed, you can see we do another test, create a new THM formation curve, and we're in great shape. We are able to punch it early on, drop our concentration, and then the curve follows the same kind of slope. So here we've got our data really following our understanding of the science, which always feels good. These aerators, a little bit different. We've got a little bit of cost savings here with these plastic pontoons. Works just great. A little bit lighter weight as well for the crane lift. And then here you can see our compliance data. So we've got THM with the system on versus the system off. This was warranted at 40% removal, came in at 53.8, and that's pretty typical of our designs. Because we carry a process guarantee, we also carry a safety factor, right? Because it's our dime. So you can be pretty confident about our designs. Energy optimization. So here's another kind of larger system that we did close to home. I remember this one well. This is San Jose Water. Great customer. We do a ton of work with San Jose. San Jose's got some very challenging water quality because they run free chlorine and chloramines both in their distribution system at the same time. So you can imagine just how complex that can be to solve for. They're a great partner for us. Here at the Rinconda Reservoir, these guys were seeing rising organics. You may remember we were experiencing pretty severe droughts back 2015, 2017 time period. So these guys were really worried about the rising organics along with that drought, and started to see some elevated THM levels and moved very quickly to implement treatment. 12 million gallon reservoir, turning over 8 million gallons a day. So once again, we need surface aeration to really hit our target level. Great reservoir to do aeration. And you can see my buddy Jimmy out there, just for a sense of scale. This reservoir is about the size of 2 football fields. Lots of surface area for mass transfer. You can see the perimeter vent along the side here. These guys have just put on a new roof, really did not want to do any roof penetration. So we designed a custom air handling system with these big duct work. And we got great results. These guys had already installed an online THM analyzer, so we're really able to get real-time data. So they're auto sampling once every 4 hours, so that's why we've got so much data here. And you can see, I remember when this came in, just being so thrilled to really see the results. You know, absolutely crushing these THMs. And there was a bunch of backslapping going on. And I remember our head scientist, Dr. Giguère, kind of was not looking so happy. And I said, Robin, what's going on? This is awesome. And he's like, no, I don't think this is very awesome at all. What do you mean? crushing these THMs. He says, well, no, we're over treating. They don't need this much treatment. We've wasted a bunch of their money. Man, these guys don't need that much treatment. What have we done? Oh gosh, all right, well, we got to think about that for a minute. Well, after we got done scratching our head, we thought, maybe there's an opportunity here to implement some active feedback control. We've got a PLC in our integrated control panel. They've got a THM analyzer that's feeding real-time data. A little bit of clever programming here, and we should be able to automatically shut off surface aerators when we don't need treatment. So we went back to San Jose, shared that kind of plan with them. They liked it. Got a very sophisticated water quality team at San Jose Water. And so they did some work to basically understand, well, what's acceptable level of trihalomethane leaving the plant? They said, all right, well, we're actually quite comfortable leaving the plant if we stay less than 40 ppb. So here you can see the results of our effort. On the top graph, we've got THM concentration on the vertical axis, time on the horizontal axis. You can see our 40 parts per billion treatment goal. And on the bottom graph, you can see the number of surface aerators on the vertical axis at the same timestamp on the horizontal axis. So for example, here on December 28th, we're not running any surface aerators at all, and our concentration is around a 30. A few days later, concentration is shooting up. We need to call 4 surface aerators to stay at that kind of 40 parts. So we run in this mode between 0 and 4 surface aerators for most of the spring. Then we get out to June and something changes. Obviously, water temperature is heating up, but probably what happened here is they switched wholesalers from Valley Water to SFPUC or vice versa. And all of a sudden, turns out we do need all 7 of the aerators that we've installed to stay at that 40 parts per billion. So we did nail the design. Just different hydraulic operation results in different treatment. And so these guys have saved many hundreds of thousands of dollars in operating costs since this active feedback was installed in 2015. I was just down in San Jose a couple weeks ago talking to the team down there, and this equipment is still going strong. If you're in the situation of, you got some water quality problems out at the edges of your distribution system, you got some high THM levels, you're not really, maybe you haven't violated, but you're worried about it. We just want to acknowledge that coming up with a plan to implement trihalomethane aeration in your distribution system can be really straightforward. Like, hey, I got a problem tank out here. I know the water age is jacked, and I know this is where I need to be to solve my problem. Or it can be really complicated and not even remotely obvious how to approach it. Once water leaves the plant and is out in the pipes, it flows in lots of different directions. And so, calibrated water models can be helpful in, coming up with a plan, but so can just taking a close look at the data. Every municipality that I talk to, spends an awful lot of money on compliance, and, you guys are sampling all the time. Most of the time, that sample data just kind of ends up in a big spreadsheet. And you're taking that information for compliance, but just want to let you guys know we can do a lot with that data. We can pull all that data into a water quality model for you guys for free. This is something that our head scientist Robin Jaguar does on a regular basis. We use a program called Tableau to do some analysis, and it's really remarkable how much information you can kind of tease out of your existing data set. So if anybody is, on this webinar is, thinking like, gosh, maybe I would like to figure this out, but it feels a little daunting, don't be shy, get in touch. We do this all the time, and we can help you get oriented. We can do a free water quality study. Won't cost you a dime. We're just gonna, we're gonna want as much data as you're able to share with us about THM levels, free chlorine levels, and we'll take that and we'll do some geospatial analysis, get it on a map for you. We'll do a seasonality histogram so we can really understand, do you have problems year round? Is it really just when it's hot out, or is it, when it's rainy out? How's that going to work out? And this is something that we've done a lot of. It's really helpful, and it's free. So there's really no reason not to take us up on this generous offer. start wrapping it up here. I can see I've got a ton of questions. Yeah, key takeaways. First and foremost, remember the Big Mac. Please, if you have problems with disinfection byproducts, do the right thing for public health. Spend the time, figure out if there's anything you can do to drop those organics out of your water. That's the first stop along the way. Just want to hit that again. Be very clear about it. It's the right thing to do. Take the time, do the work. But also remember, if you need to get back into compliance and you're under the gun, THM aeration is a really well understood and well established treatment technology at this point. We've done hundreds and hundreds of installations. We have a high level of confidence about what level of removals we can achieve. We've got process guarantees. And we've got this great technology, active mixing plus headspace ventilation alone. It's cheap, it's easy, and boy, can it fix a lot of problems. If you're not keeping your tanks full, think hard about that, because there's really no reason at this point for you to take that approach. We have the technology to solve your residual issues. We have the technology to solve your disinfection byproduct issues. And, there's just no reason not to do it. We can help. We've got a ton of experience on the small side. All this technology was developed out of the Small Treatment Technology Assistance Center at the University of New Hampshire. We love small systems. I'm very sympathetic to the challenges that you face as a small system. It's very different than large systems. But also want to point out, we've done absolutely massive scale trihalomethaneation aeration at this point. So large to small, we've got experience and we're glad to help. And then just remember, if you are, going to institute large scale treatment, think about that energy optimization step that can really put some money back in your pocket over time. So with that, I'll give one more pitch for our website. Clean Water One has got a great website. And if you haven't spent some time there, you should check it out. I think we've got close to 300 downloadable documents in our document library, case studies, brochures, white papers. We're a technical group. We really like to follow the science. We like to provide the best technology in class across the board. We want to give you guys good advice, set the right expectations, tell you what we can do, tell you what we can't do, and then follow through. So if you need help, we're a great team to work with. And with that, I will wrap it up and get into some of these awesome questions here. I can see we've got a bunch. So I'm going to start up here at the top. All right. So what are the Henry's Law coefficients for water if it's just 10 degrees C, cold water conditions? Great question. Henry's constant is definitely affected by temperature. The colder the water, the less volatile, or the lower the Henry's constant. This is something that we do look at a little bit during our modeling. But recall, we can strip the brominated species no problem with very low Henry's constants. It's just a matter of how much air we need to introduce. So there's an equation that we use to model the effective water temperature on Henry's constants. Also on the topic of temperature, important to note, I got a question from a consultant on this not too long ago. What about air temperature? Well, we looked at this fairly exhaustively in that peer-reviewed paper that I published back in 2011. We did not find any evidence that air temperature has an effect on overall removal rates. Water temperature does, air temperature does not. So had a question on concerns about THMs being introduced to the air. That's a great question. We got into this originally, gosh, probably 12 years ago, doing some work with the regulators in Southern California. And the thing to remember here is that the concentration of THMs that we're treating is not milligrams per liter, it's micrograms per liter. It's parts per billion. So, well, we're concerned about that from a health perspective, but from an air quality perspective, if you look at the volume of volatiles that are actually released, I got into this in Northern Ireland about 6 months ago because with some folks who had some questions up there, we ran the numbers again for the first time in a long time. It's generally, even for large systems, it's going to be less than 1 gallon of oil paint released per day. So Again, because our concentration of THMs or parts per billion, the amount of volatiles released by air stripping is usually quite low. And we've never yet been in a situation where the regulators have asked us to work on it. Carl, I see you. I haven't seen that name in a long time. Carl, great to see you, sir. Excellent PA, love it. Yes, Charlie, who wants more piping that can freeze anyway? Yeah, pipe freezing is a big deal for these spray aeration systems. We definitely experienced that on more than one install. And again, you know, in our experience, we fielded roughly 80 spray aeration systems and learned some lessons there. Definitely, you know, if you're a consulting engineer putting out spray aeration designs, we'd love to talk to you about that because you're not doing your customers any favors. What effect does aeration have on chlorine residuals? All right. Great question. And I've actually got a slide for that. So let's see here in the appendix here. This is from the work that I did as a graduate student, but this was a question that we had early on. Yeah, what's going to happen to your chlorine if you start, you know, messing around volatilizing trihalomethanes in your tanks? And we did an exhaustive lit review on this. Satisfied ourselves that for ions, so when you add hypo to water, it's going to speciate into hypochlorous acid and a hypochlorite ion depending on the pH. And so ions are just not volatile. So we weren't really all that concerned about what was going to happen at high pHs when we have got the ionic form of our hypo. But at lower pHs, when it's almost all in the acidic form, we found surprisingly little in the literature about what was going to happen. So we designed a benchtop experiment where we did diffused aeration, and we placed diffuser stones in the bottom of a beaker, dosed it with chlorine, and then kept the pH low by adding acid. I don't remember. I think it's hydrochloric acid, but I don't remember. It's in the paper. We pumped a ton of air through the water. We took it up to an air to water ratio of 200 to 1. So that's 200 parts of air through the 1 part of water, and continually monitored the chlorine level. And we found no effect. After we did that, my professor, Robin Collins, you know, master water chemist, much stronger water chemistry than I am. I'm more of a physics guy. He came up with some good theory as to why that is the case, and that's in the peer-reviewed paper that I published. In the intervening years, that was back in 2011, there's been other publication on this, and I can think of a couple of papers that have looked at this, and they found no effect. AWWA weighed in on this in their distribution system manual of practice. I think that's M63, 62. And they said, yep, we really have seen no signs of chlorine coming out during aeration. However, in the intervening years, I have talked to a couple of different customers, both in the Southwest, both doing THM aeration at large scale, both using chlorine gas as their secondary disinfectant, both reporting roughly a 20% drop in their chlorine residual as a result of aeration. So all the science that I'm aware of says no. I have a couple of anecdotes that says yes, for chlorine gas, we have seen a result. And so that's what I have to report on that. Great question. Let's see here. What's the expected maintenance on this equipment and estimated useful life? So our philosophy is that any equipment that goes inside of a water storage tank should not require any maintenance at all, no touch by human hand, no grease zerks, no nothing, no pull it up, no nothing. Yeah, that's the idea. Nothing should happen. Obviously, this stuff is going to die eventually. We got bearings, we got motors. It will die in time. That should be 7 to 10 years from when we actually see this stuff installed in the tank. So yeah, it should go for quite some time. All right, I think I got time for one more. Oh, it's 11. I'm going to sneak one more in here and then I'll let you guys go. Is there any smell with the ventilation of the trihalomethanes? We're looking at installing near homes. No, there is no odor associated with this. However, there can be sound. So when you're running a ventilation system on top of a tank, there can be a sound footprint that you should be aware of. We've got some math that we can use to tell you how many decibels you're going to be hearing at the property bound. And we also have sound attenuating closures that we can put around the active headspace ventilation systems, but that is something to pay attention to as you put these together. I didn't get to all the questions, but we're out of time, and you guys have been a great audience. I really appreciate it. Thanks for showing up today, and we'll keep the good content coming, I promise. If you need any kind of CDH or you need a credit for listening to this, scan that. I'll back up here a little bit. Scan this on the computer right now, and go ahead and request a CEU, and we'll get that out to you in the coming couple weeks. Thanks so much for tuning in today, everybody. Have a great one.